In this video, we will look at how the choice of approximation functions that we make for real and virtual displacements, how that choice affects the quality of the solution that we can get with the Ritz method. So let's dig in here. And first of all, recall that the approximation that we use for real and virtual displacements must satisfy the continuity requirements, which is basically that they must have first derivatives that are square integrable in the PVW, the principle of virtual work form of the weak form. Another requirement that we have on the HI shape functions that we use for the Ritz method are that they should be complete. And one example of that completeness requirement is given for example, for the polynomial functions. If we choose polynomial functions, a complete polynomial of up to fourth order will include all terms from h1 through 4. If in your approximation you are missing, let's say, the h2, the quadratic function, then no matter how many additional terms you take for the polynomial, the solution will not keep getting better and better as you increase the number of polynomials, as we saw in the example presented in the previous video. So this having the completeness of functions helps in convergence to the exact solution as the number of polynomial functions or the number of approximation functions is increased. Another thing that you may note from here is that these functions, the linear, quadratic, cubic, and quartic, and so on, these functions are, as we increase the polynomial order, they tend to look more and more like each other. So from h1 to h2, that's definitely two different functions. h2 to h3, that's not a very big change or a different function. Similarly, h4, h5, and h6, if you were to plot higher order polynomials, they would continuously look more and more like each other. So by adding functions that actually look like each other, we are not necessarily enabling the Ritz method to compute a solution that is better. In fact, this choice of polynomials, if for higher order polynomials, can lead to very poorly conditioned matrices when we are trying to solve this equation on a computer. And what does that mean? The condition of a matrix K, if you remember from linear algebra, is the ratio of its maximum eigenvalue to its minimum eigenvalue. And one way to interpret that, for just a 2 cross 2 stiffness matrix, if we are solving two linear equations, then we know that those two linear equations would be represented by straight lines on an xy plane, for example. And wherever those two lines intersect is the point that gives the solution to those two linear system of equations. Now, if a system is well conditioned, then those two lines will intersect very clearly in a single point, and the computer will be able to find that point on a computer reasonably accurately. However, if those two lines are not clearly apart, which will happen if the functions that you're adding to your approximation look more and more like each other, then the lines that you will get that represent the number of equations for your system of equations that you are solving, those equations would also end up looking like each other. And this system is an ill-conditioned system where the computer may not be able to find where do these lines intersect exactly, and the accuracy of the solution will drop. So typically in MATLAB or for most programming languages, if we have condition numbers of the matrix that are 10 to the 5 or larger, then the computer throws up a warning that the system is not well conditioned and you may not get a good solution. So the best way to keep this condition number low is by choosing H functions that are linearly independent, and not only linearly independent, but the functions that are visually even different, look different from each other. So how can we do, or how can we construct such functions, let's say from polynomial functions which are certainly linearly independent, but they don't lead to a well-conditioned system for high-order polynomials. So to understand how we can construct functions that don't look like each other or are not only visually different but also linearly independent, what we'll do is we'll draw an analogy of functions that can be orthogonal to each other. So how we know what orthogonal vectors are. If we have, for example, let's say three vectors in three-dimensional space, v1, v2, v3, then we call them orthogonal if the dot product between any two vectors is 0. And a simple example of such vectors are e1, e2, e3. Our basis vectors e1, e2, e3 are orthogonal to each other. Similarly, n1, n2, n3, if you may recall back from chapter 1 when we discussed tensors, n1, n2, n3 were orthogonal eigenvectors for a tensor. Similarly, when the tensor acts on these vectors, they map to a set of vectors that are orthogonal to each other. Now, slight differences between these sets of orthogonal vectors is that even e2, e3 are not only orthogonal, but they are orthonormal to each other, because the dot product of any two pair of these vectors is 0, but also the magnitude of each vector is 1. Similarly, n1, n2, n3 are typically orthonormal because we choose these eigenvectors as unit vectors. However, in general, when a tensor T acts on these on its eigenvectors, it produces mapped eigenvectors that are not necessarily orthonormal, that are not necessarily of unit magnitude. So these vectors, T acting on n1, n2, and n3, these vectors are not necessarily orthonormal, but they are orthogonal because the dot product of any two of these mapped eigenvectors would still be 0. All right, so we can use the same definition of orthogonality for functions, but in order to do that, we need the equivalent of a dot product for functions. So how do we do that? We do that using something called the inner product. We'll compute the inner product of two functions, hi and hj, that are defined between 0 to L on the x-axis. We can define that inner product by simply taking hi times hj and integrating them between 0 to L. And that's the inner product of two functions. So here's a quick example. Let's say my two functions are the sine of x and the cosine of x. And the domain that I'm looking at is between 0 and pi. So L is simply equal to pi. In this case, I can compute this inner product in this manner, and I find that the inner product is 0. That tells me that sine and cosine functions are orthogonal functions in the interval 0 to pi. They may not be orthogonal functions in a different interval, but in this interval 0 to pi, they are certainly orthogonal functions. Using this idea of orthogonality, we can actually create functions or even vectors that are orthogonal to each other, even though as long as they are linearly independent. So for example, for vectors, if we have three vectors, v1, v2, v3, they are clearly not necessarily orthonormal or even orthogonal. They are not orthogonal. But using these three vectors, or starting from these three vectors, can we create three different vectors which are actually orthonormal or orthogonal to each other? And the answer to that is yes. We can use a process called the Schmidt orthogonalization to create vectors that are orthogonal to each other. And the way that works is that we are going to create these blue vectors, which you can see are orthogonal to each other, from these red vectors, which are underlying in here. So the first step of that process is that the first vector, the first blue vector that we'll choose will be identical to the first red vector that we have here. The only condition on these red vectors, by the way, is that these red vectors must be linearly independent. They must not all be pointing in the same direction, or they must not, all three of them must not be in the same plane. So as long as they are linearly independent, we can create orthogonal vectors from them. So the first one is right along v1, no change. For the second one, what we'll do is we'll take the vector v2, we'll compute its component along v1, that is v2 dot with v1, and we will take that component and multiply it with a unit vector along v1, that is unit vector along v1, and we subtract that component from v2. So essentially we are taking the component of v2 along v1 and we are subtracting it out to get the remaining component of v2, which will be perpendicular or orthogonal to v1, and that's basically v2 prime. So from this v2 we subtract the component of along v1 and we get the remaining component, which would be perpendicular or orthogonal to v1. Similarly, we can we can rearrange this expression slightly. The denominator is just v1 dot with v1, so we've put that here, and this gives me an expression for v2. Similarly, if we write an expression for v3, we see that all we are doing is we take this v3, subtract its component along v1 from it, and subtract its component along v2 prime from it as well. And whatever remains is v3 perpendicular. So the v3 here, subtract its components from along v1 prime, subtract its component along v2 prime, and whatever remains is going to be perpendicular to both v1 and v2. So in this manner, we can create three orthogonal vectors, v1, v2, v3 prime, from three linearly independent vectors that were not necessarily orthogonal. And this is the Gram-Schmidt process. We can actually extend this idea for higher dimensional spaces. In an n-dimensional space, we can obtain n orthogonal functions by taking a vector in the n-dimensional space and subtracting out its component along all the previous functions. So for example, the jth orthogonal function would be equal to the jth linearly independent function minus its component along all the previous I functions, where I goes from 1 to j minus 1, which is basically what we did here as well. So this is an expression that can be used for higher dimensional spaces for vectors. A couple of things to note here. If you take the dot product of any two such vectors, just plug in into that approximation, and you will see that there is a dot product of k with k, which cancels off here, and the dot product of and this particular dot product ends up being 0, which tells me that for any two vectors k and j that are not equal, they will be perpendicular to each other. That is, they are orthogonal to each other. Another thing to note here is that these prime vectors that we created, they are not orthonormal, but they are orthogonal. And if you want to make them orthonormal, we simply divide them by its magnitude, and we get orthonormal vectors. And the same idea can be extended for functions. So I have a function hj as a function of x, and the orthogonal function is created from a given non-orthogonal function by subtracting its components along all the previous functions using the inner product definition, where these I functions are going from I from j I going from 1 to j minus 1. And you can again then create orthonormal functions with a hat on top by simply dividing a function by a scalar that is equal to the square root of its inner product with itself. So these would be orthonormal functions. And I'll let you go through an example in your textbook which shows you how to compute these orthogonal functions using this Gram-Schmidt orthogonalization process by simply looking at polynomials, fourth order polynomial with x over L equals 1, or x over L square, x over L cube, and x over L to the fourth, using those basis functions, monomial polynomials, we created these polynomial functions, which are also fourth order, but look at how different they are from each other. These polynomial functions are orthogonal to each other. And if we use these functions as our basis or shape functions or our HI functions, then the stiffness matrix K that we get is very well conditioned. Even though the solution that we get does not change, the condition number of the matrix is very good.